So yeah, hello everybody. Welcome to the first episode of RoboPaper. Very cool today to have Jiafei to talk about his latest paper, SAM2Act, Integrating Visual Foundation Model with a Memory Architecture for Robotic Manipulation. Quite a mouthful, but anyway, maybe just as a start, Jiafei, maybe you can share a little bit about yourself.
Yeah, thanks, Michael. Yeah, so hi everyone. It's an honor to be the first guest on such a interesting broadcast and sort of giving people awareness of robotics, robot learning as a whole. Anyway, my name is Jiafei, and I'm like a third-year PhD student from University of Washington in Seattle. I work a lot on robot learning. I also work on like data generation for robotics. These days, I'm really interested in building foundation models for robotics and trying to understand what's like the right form of ways of training, for example, vision language action model, and what is a good kind of representation that we should be looking for in terms of training some of this model and having a better understanding of robotics as a whole. I think that sort of interests me a lot. And same as Chris, and also I think Michael is really interested in robotics.
Yeah. As a non-researcher, as a layman,
yes,
I guess.
of course, yeah. So I think this is a really interesting work that sort of came out from my group and inspired. I guess it's not just purely from me. It's work and led by Hao Quan, who's a incredible undergrad that's able to be able to work at a capability, I think, of like equivalent to a PhD level. And so I think that the idea behind this work is really something that we have been trying to explore a lot in Dieter's group in the RC lab here, which is to be able to have a better understanding of how can we sort of build like robotic transformers, especially in like this kind of 3D based robotic transformers, to have capabilities beyond just doing multitask, but also having the ability to generalize to a diverse kind of environmental perturbation, to be really robust when you change lighting, change table texture, and also to be able to perform manipulation on like precise objects, or even to be able to do high precision manipulation. And also one of the most important aspects of what this paper tries to address is the idea of memory. So I guess like a lot of times like previous work coming from our group like Clipper, Percival Actor, I think a lot of these are really excellent work that sort of opens up a new field, opens up a new way of looking at robot learning, and also that lead to like really impressive work such as RVT, RVT2, and all these kind of 3D based behavior cloning methods. So inherently there is a lot of problems, and as all these different iterations of BC policies that came out, it tries to improve and try to address some of these problems. So are we. So we also believe that maybe there's a way that we can go about building such a robotic transformer based policy in a way that's able to be really generalizable and able to perform multitask, and is also able to solve some of these high precision manipulation tasks, and ultimately to have the concept of memory. So I keep mentioning memory. So what I mean by memory in this context, I think would be more of the term whereby if you try to train a behavior cloning agent, you do not just want it to sort of memorize the data, because there will be times where you hit a state whereby it's hard for you to determine what is the next state, and that sort of is the idea here, whereby, for example, if you go do a task and you once you're done with the task, you go do something else, and then now you're coming back to this task again, will you be able to recall? So this is something that's really intuitive to humans, but a lot of times this kind of VC models tends to fail in terms of doing such tasks. I think the fundamental problem is that such tasks breaks the Markov assumption, whereby your current observation sort of helps to predict the future state. So if you come back to the same observation, then it's going to be really difficult for your model to sort of adapt to that. So I think that's like the high-level overview of SAM2. And I'd like to also go into the details to talk about how we sort of achieve that. So yeah, Michael, I think if you guys have any questions, we can discuss and we can chat more about it. But yeah.
Yeah. So why do you think you need this separate memory? Why do you need a separate memory-based architecture? Why can't it just have like a really long context or something like that? Is there a...
Yes. So I think that's a good point. So I think you can sort of also look at a problem whereby you have a really long context. But I think the idea here is that we realize that that will essentially also lead to some form of compounding error. And so when this kind of compounding error sort of occurs from BC training, you realize that, okay, how can we sort of get out of that loop? Because essentially you're still relying heavily on the distribution of your data. So that is something that is not that intuitive. A lot of times it's hard for you to really evaluate whether is it a long horizon task that is the model failing just because it can't do the task, or does it really not remember what you have done? So there's a lot of design aspect that goes on into behind SAM2Act, whereby not only we propose the model, but we also propose a benchmark on top of that, because essentially you want to have a way to systematically evaluate policies on just memory and not penalizing them because they fail to perform the task. So when we design some of these tasks, which I can scroll down. Okay, so when we design some of these memory bench tasks, we look into the fact that, we want to make sure that, any kind of like BC policy, once you train it with enough data and it's really sort of overfitted to the task, is able to successfully complete the task. And the only point of failure should occur is at the last step where it makes that decision. So the idea behind this memory task, as you see, we have like 3 tasks. And the way we sort of go about designing these tasks is also pretty clever. I think Chris here is probably very familiar with this benchmark that came out from Dyson, I guess previously Stephen James, which is RL Bench. So RL Bench has a huge array of over 100 tasks. And obviously, if you're just training and testing on some of these tasks, even though the sequence length is really long, you can't really sort of evaluate memory. So the way we sort of look at this problem is that let's make the tasks as simple as possible, but yet try to bring out the nature of, our policies able to have that kind of implicit memory. And in this case, we are focusing a lot on spatial memory. So when we try to design these tasks, we look at those axes. So the first task we actually try to design is the one over here, which is the idea whereby the drawer, so it has 3 levels of drawers. And in the training data, it can be any of those drawers that's originally open. And the policies of the robot is given demonstrations where the robot closes the drawer and then reach for the button and then try to reopen the drawer, based on what was initially opened. And the way we sort of design it, we design in such a way that the language doesn't give away if you think about the drawer, it's actually more of along the z-axis. So it's like a spatial task whereby now I'm trying to evaluate based on the z-axis of like whether can the model predict the variations. And the why we design the button is so that when the robot agent sort of remembers to press the button and it reaches a state whereby it's hard for it to determine whether which state was previously where the drawer is open, that sort of breaks that Markov assumption. So I think that's the way that we go about designing. And interestingly, which I show a result later, models actually succeeded in the task. But most of the time when it fails at the last step, which is to choose which drawer to reopen. So in an intuitive sense, then that would be 33%. But after that, if you look at the result, you realize that there's some noise to that, because I guess a huge portion is because when we generate the data, we didn't make sure that the data is, implicitly balanced out. Somehow the behavioral cloning policy tries to, you can call it like hack it, or sort of like tries to overfit to a distribution that more likely to open the top. That's why you will not get an exact 33%. But our model is able to achieve close to 100% success rate for this task. And when we design the center task, which is, initially the cube will be in any of these square patch, and then the agent will first pick up the cube, put it into the center, and then press the button. And at that point, it breaks the assumption, and the agent need to be able to determine which patch was the cube originally at. So if you look at this is along the X and Y axis. So this is the idea of how we show along different 3D axes will we be able to have that spatial memory. And the last task when we design is actually based on like a very real world scenario. So I guess when everyone tries to, soup, you will try to add salt. So if you don't want your robot to be always adding salt over and over again, because it might not remember exactly how many times it adds. So in this case, we do the counter reasoning. So whereby initially you have a cube that's set in the center, the agent puts the cube into a patch and press the button. And now at this point in time, the agent has to choose the alternative cube rather than the cube that was, first originally set. So that gives the illustration of like the example, the sort of the illustration I just mentioned, which you want to add salt and you want to add your pepper. You don't want to keep adding the salt over and over again. And later I can show a few more examples on how different policies behave when evaluated on our memory bench. So this is like a high level idea of what goes into designing such a task and why it's important that you can't solve with long context.
I really thought that this was one of the parts that I thought was really cool about the paper, actually, because I feel like if you haven't worked with many of these imitation learning methods, like you almost always have it set up so that it is very Markov. meaning that like you can tell exactly what is going to happen given the frame. And
Exactly.
and in addition, there's all these data, the biases, like you said, like you were saying, where it's not always the same drawer, like that kind of thing, like making sure that every task is like perfectly well balanced and all of this so that it can properly learn based on these. That kind of stuff is near impossible with real robot data. So anyway, I don't want to just tangent too much, but
Yeah, exactly. So I think to add on to your point, it's really tough for us to actually design such tasks because we want to make sure that the underlying assumption that the policy is able or capable of succeeding, and the only reason it fails is because of memory. That's something that's really tricky, and that requires a bit of fine tuning. Not fine tuning as in fine tuning the model, but requires us to sort of tweak the way we design that task. But the overall underlying principle is along this line. And also we realize that as the sequence length gets longer and longer, which what you mentioned, like if you have a longer context, can we also use that to evaluate memory? The answer is yeah, sure we can. But the problem is that there's a lot of chance that the policy fails not because of memory, but because it just has that compounding error from behavior cloning. So I think that is something that inherently I think is hard to address. One thing that we make sure is that it has very short keyframes. So basically it has about 2 to 3 keyframes to memorize, so making the task much simpler and decompose the task to be easier so that we will focus primarily on memory. Obviously, the policy also we evaluate on like general RL bench 18 tasks to see whether it's general manipulation capability.
So let me just a quick follow up on that. So
Okay.
What actually is a trajectory for you? So in this case, and particularly for people listening, like what? Like you mentioned keyframes. So let's explain like what exactly is coming out of this model, right? Like coming into it.
That's a good point. Yeah. So I think there is like there's a line of work with like visual motor policy, and there's a line of work with what Mohit sort of started with like perceiver actor, whereby in this case a keyframe is basically in the context of like a 6 stop pose, and then basically you are bridging between the keyframes through a motion planner, and that makes it decomposes the problem to be easier, but also there is also its downside or limitation where it's not that reactive as compared to an action-based model such as like diffusion policy or action chunking, where you're always consistently predicting actions at a fixed frequency. So I think there is trade-off, but obviously for like keyframe-based method, especially like perceiver actor or like RVT, they require some form of 3D. So to do that, you need to be able to calibrate your camera. You need to be able to have a good RGBD camera setup. And then also the good side about that is you require less demonstration as compared to a 2D based model. So there is like a trade-off to that. And I think for us right now, we are focusing on a keyframe based approach whereby we predict the next best keyframe, and then we sort of move the robot there using a motion planner or motion primitive. So yeah, thanks for pointing that out, because I think I need to give the audience some context.
Yeah. Well, you can also go to I think this diagram. This is what I was gonna
So I think to sort of go in depth on how SAM2Act work, I think it's also good for people to know like just in general this line of work. So SAM2Act, it doesn't just come out of nowhere. It's obviously as we are doing research, we're always building on top of the shoulders of the giants, and this SAM2Act was built on top of RVT2. So RVT1, then there was RVT2. So maybe also to give the audience a bit of context, RVT1 is basically a multi-view transformer, robotic transformer that takes a RGBD scene that generates point cloud, and they re-renders the point cloud into multiple virtual view, and they have a multi-view transformer that tries to learn to predict a point on all these individual views, and that point sort of acts like action heat map. And when you sort of bring all this action heat map back, you get a point in 3D space, and then having a motion planner to move to that point is basically how you sort of predict. And the idea behind RVT is to sort of increase the speed of training for models such as perceiver actor, which is in voxel space, so which is really hard. It takes a lot of computational, it takes a lot of compute and time to sort of train. So they sort of outlive that into 2D so that to make the training much easier, or 2D in that case.
Yeah, so Jiafei, so when you say multi-view, you literally means from a RGBD, thing, and then the point cloud, and then the multi-view literally could be arbitrary. It could be like from the side, from the front, from the top.
Yeah, so
is that what you mean by?
Yeah, correct. So the way the RVT does is that it takes RGBD and it projects into point cloud, and it does a virtual re-rendering. So I think they re-render in a way that's orthogonal to each other. So they have a view from the top,
I see.
from the left, from the right, from the side. Obviously, the thing about this kind of re-render virtual view is that there might be like some form of like, missing
Occlusion.
pixel, resolution issues. But, the idea here is that now we are taking this 3D and we are uplifting it into like maybe a 2.5D-ish kind of image plane. So the idea is that you're only doing prediction on this image. So in that context, then it makes the training faster. So we draw upon the idea of what RVT does, but obviously not the first RVT because as research, especially in robotics these days, model comes out really fast. So by at the point we are doing this, there was RVT. And RVT2 sort of brings along the same idea, but the thing that they sort of do is that they do a cost to find approach, whereby they do this RVT transformer twice. And the first time, instead of predicting a point on the heat map, it predicts sort of a point of where a region should be. And then it sort of crop inwards into the point cloud and takes that point cloud and re-renders again. But now you are zooming in, and that's like the fine. So the fine stage will do the exact same action twice. And they realize that by doing this, it will actually help to improve the prediction of the action heat map and ultimately lead to a better performance for the model itself.
So when I was reading the paper, I have this question like this cause and fine. I know this is not your paper you're putting on top, but I'm just curious, like, is a design decision that's made by the researcher, right? So where do you draw the line between what is cause and fine?
I think it's, I guess the zoom in part is sort of like heuristically defined. So like probably if you find a region that is sort of, I think the high level intuition is that, if you're just predicting, you try to predict the next action based on a current, point cloud from like the RGBD camera, you might not be able to see that clearly. So the idea is that now if we want to, because the original word, the first word is called perceiver actor, which is to perceive and to act. So once you zoom in, you're able to see clearly, and then let's do another round of that prediction to get more more fine point, and that fine point will ultimately lead to better performance. Also, they also show that it's good for like precision tasks. Our approach show that it's even better. Our approach show that it can do even much more fine-grained manipulation.
So it's largely just like an efficiency thing then? So saying that like we have, obviously the camera can capture a much higher resolution than you usually feed into a transformer. And so is that like, so I'm doing this all in software essentially. I'm taking a higher resolution image, I'm downsampling it to like 640 by 480 or something. And then I'm choosing an area and then I'm blowing that up to be whatever, 640 by 480 again, but whatever maximum resolution, that kind of thing.
Yeah, I think that's the case. I think Ankit's from Princeton, he works a lot in computer vision, and like this re-rendering technique, I think was used in other work in his PhD. So I think this is a technique that probably people in computer vision use quite a lot. But I think this is like sort of like one of the first times where you sort of translate the idea into robot learning. And I think it works really well. That's the outcome. So to further add on to Chris' point, so with that intuition in mind, so we ask ourselves, how can we make this better? So to make this better, we need to probably do two things, right? Because a lot of these RVT per style models, they are not sort of, I guess they don't have some kind of like pre-training visual foundation model in them. And a lot of things sort of is trained from scratch. So there is a lot of missing components in terms of, semantic understanding that comes from all these visual encoders are not being able to, be well utilized. And I think there's a huge line of research like 3M, MVP that shows that this kind of, pre-trained visual encoder does help with robot manipulation. And I think that's the idea that we want to draw about. And also the next thing we look at is, okay, since if RVT is already doing cost to fine, can we make the resolution even better? Or can we improve the resolution so that it can capture even more fine-grained details? Or in another way, instead of making it better, let's think about every time when you sort of zoom in, or every time when you do like convex upsampling, you are losing information. So is there a way for us to retain that information as you are, going from cost to fine? So that's all give us ideas to sort of think about. And then I guess a lot of times when doing research, you have to be at the right time, at the right place, when the right things came out. So I think that's where SAM2 came out. And that's where, we see an opportunity. So that before this, there was a work called SAM embodiment, which is SAM-E. So the idea of SAM-E is basically taking RVT, and the only thing they sort of really try to do is to, before passing into the multi-view transformer, they have a SAM2 image encoder that sort of, output image embedding that is really rich because the SAM2 encoder is pre-trained. And then using that image embedding, they train the multi-view transformer, and then everything else is basically RVT. So that's what they did. And they show that performance increase, the model gets slightly more generalizable. And so we believe that the same idea will work with SAM2. So the first thing that we did was that, okay, we are also using SAM2 image encoder that takes
So what's special about using SAM2 here? Like why is it important to use SAM2 over
So that's a good question. So I think first of all, SAM2 image encoder from the original SAM paper, it has shown that it's better than the first original SAM1 encoder.
Yes.
That's like trivial. Yeah. Yes. But the second thing that's really interesting is that only SAM2 image encoder give multi-resolution embedding. So that's something really unique, and I'll come to why that matters. So that's like that's the two reasons. So with the SAM2 image encoder, we are able to sort of encode the image that's passing into image embedding that's really rich, and this image embedding comes in multiple levels of resolution. So this is the cool thing. So like as what is mentioned, why SAM2, right? So besides the fact that it's better, it also output this multi resolution embedding. Yeah, 16, 32, and 64. So this multi image embedding is sort of captures a lot of information from the original image that is sort of being encoded by SAM2 encoder. And this information are stored in a very different way. So for example, it can be, a certain dimension whereby, if you change the lighting, some of these embeddings are not really affected. Or if you change the texture of the table, some of these embeddings still retains the visual information from the original image. So I think that's also one of the reasons why our model is much more generalizable. But before that, with the output image embedding, we feed into the multi-view transformer, which is still pretty much the same as RVT2. It comes to the next part, which is how do we do that convex upsample? So the original paper RVT2, it does this convex upsample so that it takes a dimension of 128 by 16 by 16, and they sort of upsample it to become 1 by 224 by 224. So that's basically like the image, and where a point lies there, that's sort of like the heat map that they're trying to predict. And to us, we look at, okay, this heat map looks awfully similar to like a mask, for like segmentation. So I think that's something also inspire us to sort of look into SAM2. And we realize that, by just doing one-time upsample, you basically lose a lot of information in this process. So how can we sort of make sure that we don't lose the information? We decompose them upsampling process into 3 different stages. So at every time, we only do one-time upsample. And then after you do first upsample, it becomes a 64 by 32 by 32. And then you sort of have an element-wise addition with the ResNet 30, which sort of adds the information back as you are continuously upsampling this. So in this process, we realize that informations of the image features are not lost. So when you sort of upsample all the way until you predict the heat map itself, actually makes it much more accurate, and it also makes it it also increase the performance a lot for the manipulation task itself. So I think these two things happen together. That's why it makes it work. And I think if from our ablation, we show that if you take away these two features, if you take away any of these features, it will not work. So I guess that's also a component of being at the right time at the right place, and also to have a better intuition of how we can integrate SAM2 into an existing architecture such as RVT2 also makes a huge difference. Yeah.
So just to summarize, so the multi-resolution training in SAM2. So SAM2 is segment anything 2, which is like from Meta, like really useful model for all this kind of like video and for segmentation. And then so you have trained this multi-view transformer. Transformers are generally not trained on huge images for obvious reasons, right? It takes a lot of tokens, very slow. But what you can do is that and the action space, importantly, which I think is different from what a lot of people usually see, again, and maybe not usually, but like I think is the action space here is a heat map. So it's saying the actual positions that the robot is going to are abstracted out, right? It's going to so I need a very accurate heat map, which is saying something like, I need to pick out this very fine detail from like the handle on this cabinet that I can go and reach the robot to. And so by doing this with these pre-trained features and this multi-view transformer, I can then resolve this very complex problem of figuring out all this language and this like long horizon memory and spatial reasoning, and get this perfect, extremely accurate segmentation of the thing that I need to move to, which, because I have a 3D map, I can then just send my robot to and act on. All right.
Exactly. Yeah.
Okay.
I think that's a really great summary, and I think the intuition behind a lot of this from past work also sort of draws upon that. And I think the idea is that if the better that map is sort of constructed, the more accurate is your robot able to reach that point. So if any information is lost along the way as you are trying to draw this map, essentially you will have a huge impact on the performance of this car model, especially it's purely trained on just demonstrations. So I think that's one of the intuition. And so when we are done with this SAM2Act, this is like a general model architecture. And let me just go back. Sorry if I had to scroll. So the idea is that when we did this, we obviously did this for both the cost and fine. So that's what I call stage 1 training. So we are able to train SAM2Act, which is really for general manipulation tasks. And it's able to do multitask, and it's able to, be able to be highly robust or generalizable. And it's also able to, perform like really precise tasks, which previously a lot of the models fails to do in our bench. So that sort of gives us a really good general manipulation policy. And then it comes to the next part, which is how do we incorporate memory into that? And we realize that you can't really train everything in first stage, because the idea of memory is to sort of retain temporal relation. And it sort of contradicts the normal ways of, what Stephen James and a lot of prior work from like Percival or RBT sort of they propose, which is that, you want to sort of randomly take a keyframe and try to predict the next best action. So if you are feeding it sequentially, then it's going to hurt that process. You're going to hurt your model because you'll probably be overfitted to that sequence. That temporal relation is good for memory, but it's bad for performance. So that's the idea. So when we try to train stage 1, we realize that if we combine the idea of temporal into stage 1, the model's performance in general manipulation really decreases significantly. So the idea is that let's break it into 2 stages. Stage 1 is purely to train the general manipulation policy. And then in stage 2, we are going to freeze some stuff. So what are we going to freeze? We're going to freeze the SAM2Act image encoder. We're going to also freeze the multi-view transformer. So these 2 things sort of learns the action from the first stage of training. And then we look into, okay, what do we want to add in? Because SAM2 have this memory mechanism, and this memory mechanism contains a memory encoder, memory bank, and memory attention. So we want to integrate that into this architecture. But you can't use any pre-trained one, because you can't use the pre-trained encoder, or even some of the pre-trained memory mechanism, because what SAM2 is trained on is totally different from what we are training on. Because they are training on memory of like mask, segmentation mask and all these things that they're tracking. But for us, we want to track points, which represents action. So that's inherently still different. So we are thinking of, okay, if we can't do that, we have to fine tune the whole 3 components, then let's do it. And the way we sort of do it is that, we have this architecture whereby we only care about the cost branch, because the idea is that once you're able to determine memory, or you sort of remember which region to look at, the fine branch will solve by itself. So because the fine branch basically predicts, like what Chris mentioned, which point of the mark. But if you are able to zoom into that region, that means you already remember exactly where you are supposed to go. So that solves a huge problem. To sort of go about doing this, what we do is that now for the second stage of training, we are feeding data in a temporal manner. And because it's a multi-view transformer, there's different viewpoints. So we actually essentially have 3 different, memory bank. So we initiate 3 different memory bank, and every pass, you sort of cache the observation or the keyframes after they comes out from the multi-view transformer's prediction to try to attend with whatever is inside a memory bank. So at the start, there's no memory, there's no observation that's stored. So after a few iterations, every time when a new observation comes in, you will always attend with the past memory that was cached in the memory bank. So by doing that, every time before it predicts the heat map, the output of the originally from the multi-view transformer now is memory. So it actually helps when you upsample it back into predicting the heat map, it will actually sort of remembers, like previous action. I'm here. So based on the data that's trained on what is most likely to be the action that I'm supposed to go for the next one. So I think that's a really interesting idea here, and the way you put this memory mechanism makes a huge difference. We have to put it after multi-view transformer instead of before the multi-view transform, because we want to sort of learn at least the first layer of prediction, like where we want to go to, and then sort of attend that to the memory bank. Attend that with the memory attention by taking out the cache memory from the memory bank.
Why does it need to be after the upsampling though? Why can't it just be like there's I don't know. Why does it need to upsample before it gets encoded into memory?
Yeah. So so that's a good question. So I think why after is because I think we try both and we realize that putting it after is better, and also intuitively to think about it is that you want to sort of at least learn to have idea of where you want to sort of predict to, and then drawing on the idea before you sort of do the upsampling, attempt with your past memory, so that now when you are trying to upsample, that thing that you are sort of upsampling contains or sort of like enriched by memory, so that memory comes from this memory bank. And we also realize that obviously the memory bank has a fixed length, so obviously the way we sort of decide this is it's not task specific, but for like multitask we will take the longest sequence of keyframes to use. And the idea here is that as long as if you are doing multitasking, you take the longest sequence to use, you will definitely have enough for sorry. Okay.
No, so the idea is that the multi-view transformer, again, it's just like that's just like a snapshot. It's saying like this is the thing that I'm predicting on.
Yeah.
Then we have you go into the memory attention. So now I'm looking over basically whatever memory I've decided is important. And the idea is that the upsampling is kind of then it's kind of doing some essentially some spatial grounding of this into the image, and then re-encoding that back down. That's your
Exactly. Yeah.
Still feels like you could do this without the upsampling, but I guess I do see how that would be useful, I guess. Doing some
I do agree. Yeah. Also we realized that, obviously because at the very beginning the memory bank is empty, right? So whatever you sort of attend, is less effective because everything is sort of concatenated together. So as your memory bank gets richer and richer, the memory feature that sort of comes out after attending with the memory attention gets much more richer. And then when you upsample, that's why that's also why we design the task that the memory decision happens at the last few steps rather than at the very beginning. So that's also a clever way of thinking this, because if you happen at the very beginning, then there's nothing much to what you remember is probably the last frame. And a lot of other models could also essentially make a really good educator guess, or you have like somehow rich features in the image embedding that was used to train. So I think that's one take to that. Yeah. Yes, Michael.
Yeah. Quick question. So you mentioned that it has a fixed memory window length, right? And you mentioned somewhere in the limitation or conclusion section that you think it would be good to have varying length. Can you just elaborate a bit more, like what is this fixed window length like? What is it measured in?
Yeah.
Is it measured in keyframes or is it measured in time?
Yes. Yeah. Thanks for the question. So I think right now that's also one of the limitations, because as I was explained to Chris, this fixed window length is basically the same way that SAM2 originally did that for their paper. But I guess in their case, it's easier for them to define like a fixed window length because they are tracking like temporal frames. So that is easier. But for us, it's a bit difficult. So in this case, the fixed window length is corresponding to the number of keyframes for each of the tasks. So for example, if you have a task that has 10 keyframes, then the window length will set it as 10. But if you're training like multitask, some tasks has 10 keyframes, some has 6 keyframes, some has 5 keyframes, then we will always take the longest as the window length. So hopefully in the future, we hope that we have better ways of doing this, because essentially what this means is that you need to sort of know ahead of time how many keyframes your task has, which that is not that feasible, especially especially in the real world context, because it will vary. Like it definitely will vary.
What happens if you give it too many? Like if it the maximum context length is too large, do you see performance degrade?
So that's a great question. We are actually
too much memory.
we try to do that, but the problem is that also as your keyframe increases, the task complexity gets harder. So a lot of times it fails not because of the memory, so it fails because of a lot of action. So this like you get what I mean? It's like this.
I guess I'm wondering like if you do a really simple task and you give it just like a maximum memory of like 20 frames or something, would that prevent it from performing well?
Giving it in terms of frames or in terms of keyframes? So right now
keyframes, yeah.
A really simple task, but so I think in this case, like sort of redefine the complexity of tasks is based on the sequence of like number of keyframes in the data. Right? So if your keyframe is really long, then obviously you have to be remembering which action, like what's the next keyframe, and then if let's say that context gets longer and longer, then the performance essentially also decrease over time. So that's hard for us to distinguish. So that's the reason why we didn't try that. But I guess a good point. I think this is something that we will definitely look into and have some kind of evaluation on that. Because ultimately we want to have this memory not just for like short horizon tasks. Although short horizon task is important because sometimes like it's a split second kind of thing. You do something else, you comes back to it immediately. So I guess that's also possible. But you also want to be able to remember, if I do something, I go do something else, I do another thing, and then I do something else again. Can I come back to the first task and remember what exactly happened?
Okay.
So I think that's something that we want to extend towards in the future work.
I mean, another thing that comes up a lot in real environment and real robot use cases, I think, is just like there's distractor tasks. Like it did something totally unrelated before your thing begins, and you don't want that to actually impact performance, right? Like it's particularly for a robot in a home or honestly anything, right? So there's
exactly. And also I think like it's even harder for like robot at home with like mobile manipulation, because you need to you're also navigating, and you also need to remember where exactly you have been to, what have you interact with and all these things. So I think that problem formulation is much harder as compared to right now what we're trying to show, which is tabletop manipulation. But I guess some of the ideas is transferable and could be, applied into other contexts. And I think I have also seen previous work where people try to address memory, either from like Peter Stone or even from like Tucker, whereby they sort of decompose the problem to be much simpler, either in terms of like a grid word setting. So we are trying to push that to a higher dimension with like, with this kind of real robot embodied agent kind of approach. So there's that. And maybe I can show some cool demos. Okay, maybe before that, let's talk about a bit about the
let's talk about benchmarks. Results.
Yes. I think that's something. I think that's something like a lot of folks care about it. I think also like I think result is a good point because people build on top of each other and we are able to improve as a community. That's why I think benchmark is also very important, and that's why I also do some work on benchmarking. So the first result that we have is we validate on our bench. As I mentioned, our bench is like over hundreds of I guess tabletop manipulation tasks that was designed, hand designed, and then you have ability to generate demonstrations in simulation to train policies. So it all started with like Mohit, doing Percival Actor, and he chose this 18. I guess I asked him back then, he chose it randomly, but I guess that has been like the industry's, I wouldn't say industry standard, but academia standard, where everyone is evaluating on this exact same 18 tasks, which sometimes I also question like why this 18? There's no real reason.
But I chose them randomly, and Mohit's paper got a lot of citations. Therefore, that is the standard now. Why just those 18? Because some of the tasks in our all bench are a little bit flaky, and that's why. No.
I totally agree. That's why till this day I'm still like asking why this 18 tasks. So anyway, right now, the state of the art method I think recently is like a action-based model, ARP or something. So for them, they managed to push the score up to 86%. So for some context, when the first paper that sort of started on this 18-hour bench task to evaluate the 3D-based behavior cloning policy, it was only an average of about 60%. 60-ish%. So you can see as a community how far we actually push this number upwards. And we are fortunate that SAM2Act is able to outperform all the methods and become the new SOTA in this 18-hour bench task. And I think what is really interesting is not the fact that we are the new SOTA, but some of the tasks has a significant increase. So for example, insert pick and also like for example sort shapes. You can see that the result from the second best model, which is RVT2, it doubled. Like that's significantly a huge boost in performance. Whilst the rest is pretty much close the same. I mean, like push button is a really simple task. Most of these model gets 100. And for sorting shapes, it becomes like 64, which is like a huge boost. So I'm going to show everyone what the task looks like, and then I'll explain a bit more.
Yeah, I do like that a lot of these are not just pick and place too, like the sweeping task and so on, turning the knobs. It's one of the nice things about our bench is that it has quite a variety.
So let me show the insert pick. Okay, so this is the insert pick task, and if you look at it, you realize that this actually is one of those high precision tasks because there's only a certain region that you can sort of place the robot above the pick and before you let go. And anywhere that's beyond that, although people say that the physics in our bench is not that great, but it's not possible to do this task at all if you look at all the other models because it's really hard. to actually get the very precise position of your gripper before you let it go. On the left is what our model is able to do, and on the right is the baseline, which is in this case RVT2. So RVT2 is also known for high precision tasks, and I guess like clearly in this simulation, it shows that by incorporating the multi-view upsampling together, I guess it's mainly because of multi-view upsampling, we're able to predict much more precise action heat map as compared to RVT2, and that led to this performance. And also for the sort shape, if you look at this, okay, this object drop, but it's okay, the object is not part of that. So I think in RVT2 case, it sort of like struggles and and it failed. Oh wait, I guess that's the actual object. Okay, that's
it does run into the box a little bit on the left and yours, but it doesn't. It's not fatal.
Yeah. So
hey,
so as you can see,
Jiafei, you want to share the place cups one? I'm curious about the place cups one because in terms of just absolute success rate, right? It's 47%. I'm just curious, what is that task like? Why is it so hard? I mean, you guys are already the best.
Yeah, that's a great question. So first of all, I think that this place cup task only succeeds when all 3 cups are placed. And I guess Chris can relate to me. Like this is a really quite iconic task in tabletop manipulation, and it's really hard because you need to not only make sure that it has to be precise, you also need to make sure that the orientation of the gripper is in the right position. So you can see the baseline is really struggling to even do anything remotely close. And I think like based on our result, we can see that perhaps was like 2% when Mohi first started this. So I guess that is like a really huge improvement in terms of this line of work. Yeah, this is really tough in real world. Not gonna lie. And okay, to further, since we are already here, I want to talk a bit about like how do we test for this in the real in real world context. Obviously, simulation is good, but we want to be able to show the same result in real world. So the idea is that to do real world, we also collect demonstration in real world, and then we train SAM2Act policy in the real world. So to sort of evaluate the task in real world, we have these tasks. I guess this task is really difficult because you have to, first of all, predict a keyframe that's so precise, and when you close the gripper, I think it's like a maybe like 5 mm offset. If you miss by 5 mm, you are not able to grasp on that at the very tip of this lamp to sort of perform your next action. So the baseline is it just missed by a bit and it failed. And the cool thing about this is that even though when our model hits the lamp, it's still able to accurately predict where the point is supposed to be. And I guess maybe I can show a few different versions. Yeah. So for this one, if you off slightly, you are totally going to fail in doing that task. In all the gripper open close, that's just something that we started to activate the model. Yeah, so I guess this is one demonstration of high precision tasks that we talk about a lot in our paper. I think this is really interesting.
How many examples did you train this on?
Oh yeah, so that's a good question. So unlike action-based model, which has its advantage to be able to infer a frequency and make it much more reactive, we train this with like since it's a 3D-based behavior coding policy, we only need about 10 demonstrations as compared to maybe something like, I don't know, like a diffusion policy, which needs about 50 to 100 demonstrations. Yeah.
And then I saw that you did like 10 in distribution and 10 out of distribution.
Oh, yeah.
That's for evaluation,
yes, exactly.
Right?
Yeah. So for out of distribution, the idea is that SAM2Act is trained purely on. So SAM2Act is purely trained on data that looks like this. But during out of distribution, that's where during test time we introduce other factors. So in the real world, of course, there's not just going to be only one lamp. There's going to be a bunch of other objects. People are going to people will come in and they put random objects. So can your policy be able to still generalize on the task that you learn? So as you can see for the turning lamp task, RVT basically thinks that probably this is the lamp because it looks exactly the same color. So and predicts a point towards that. Whereas SAM2Act is not really affected by that. I guess there's a lot of a lot of the reason is due to the pre-training image encoder, because I guess it has seen the concept of a lamp, at least in terms of the image embedding that sort of output from the image encoder.
So would you say is the rest of this? So I was going to ask if this was partly because of the heat map action space, but I guess RVT is using that as well. So this is probably because of the
encoder.
Yeah, the encoder pre-training SAM.
Yeah, which I can talk a bit about the results later from the simulation experiment. So I think in this case we show that robustness. Also another way to look at this robustness is if you change the texture. So that table texture is totally out of distribution. You can ignore this part because we actually crop out the 3D scene. So that's totally out of distribution. Gravity basically did not move because it's so far away from what I was originally trained. So you have no idea that this scene is basically the same scene. It's just that I put a different table mat. Yeah. And obviously another huge thing is about okay, this is lighting, but also, obviously we also test different camera pose. And so this one we introduce an extra lighting to sort of lit up the environment so that, it makes the data, the test data set to be out of distribution from the training. Yeah.
Yeah. So Jiafei, I have a question about, so you have 4 tasks, right, for this real world evaluation, and then you have 10 in distribution 10. So it sounds like you did roughly like 80 evaluations in the real world.
Yes. Yeah.
And each of these evaluation takes like maybe a minute, maybe something like that. I'm curious, like, why stop at 80? Or do you think 80 it gets you, like, why don't do more so that you get maybe something that's more statistically significant, that sort of stuff? Or is it
that's just a good question.
Costly to evaluate things?
Yeah. So I think if ever you have a chance to work with robots, the hardest thing to do is actually evaluation. I would say like real world evaluation. In the real world, it's really tough. Because first of all, you need to ensure that the way you evaluate is fair. The same setup need to be able to reproduce for different model, and also you need to test different model, right? And obviously it can't be. I think like Russ Tetre talk a lot about like the way they evaluate models in TRI, whereby they do blind evaluation, means people have no idea which model they are evaluating. So I think that's a really fair gauge. So I think and it's also really hard for anyone to reproduce my result in the real world, because the real world has so much difference in terms of setting. You have to recollect the data again. But I guess what the real world sort of reflects is sort of aligns with the results that come from simulation. And the simulation is what we want it to be reproducible, at least when it comes to this line of work. Yeah.
So, I mean, I saw that in simulation, you guys roughly do 80+%, although that's on the R bench, maybe it's like different tasks here, and then 70% success rate here, right?
Yeah.
Would you say those like 20 to 30% that is failing in simulation, and then those 30% that's failing, let's say in real world, are they failing for very similar reason? Like, do you have some gut feel around that?
Oh yeah. That's a good question. So we didn't add that into the paper, but we did record down some of the failure case, and I think and to answer your question, yes, we see similar trends of failure. So failure, like for example, miss the grasp point or miss to predict the next keyframes with like offset. And also, I guess, like in terms of environment perturbations, you can cause the policy to choose a different object. So since you're on the topic about evaluation, I'll talk a bit about how we evaluate generalization in simulation. Colosseum is another work that I work on. So Colosseum is basically building on top of our bench. So imagine the 18 tasks. For every task, we can systematically change perturbations. That means we can change lighting, we can change texture, we can change size, we can change color. We can change a lot of these things during test time, but you are still training with the same data. And then we want to test whether how robust is some of this model to some of this change. And this is an example of like extreme case where we basically do perturbation to everything. Like if I show you the original task, you could not even recognize it's the same thing. Like as a human, I cannot even recognize. And that's what SAM2Act is actually performing in terms of getting the task done. So you're still able to predict the point, and you're still able to close the drawer. So I think that is actually coming back to Chris' point, which is that it's largely because of the image encoder that was used to generate the image embedding, and also I guess like it has to be able to even to do some of these tasks. So a lot of times when policy fail on Colosseum, they fail to generalize, and one of the main reasons we realize is that they're not that capable in terms of doing the regular tasks. That's why when it comes to perturbation, it makes things even worse. So a policy that is able to do the regular tasks usually tends to do better for generalizing to some of these perturbations. To answer Michael's question, I think obviously we are not able to do that perturbation in the real world to keep changing lighting, has a bunch of different colors, but we can do that in simulation. So I can just randomize a different episode. Now the lighting changes, or I randomize a different object. I'm not sure you can see the cup, but the texture of the cup changes, or even in this case, I think the size of the ring changes. And if the size of the ring changes, means that your model must be robust enough to have some concept of equivariant to predict points that has some offsets from the original point.
And in that case, it wasn't even trained on a range of different rings, right? So this is again a functional. Yeah.
So this is a function that came out of there. So I think one of the very typical example, or like classic example that we test for this is that in Colosseum, we will scale the size of drawers. So if you scale the size of the drawers, the position of the handle will vary. That means originally the point where the drawer was supposed to be pulled is here, but because the size of the drawer shrinks, the drawer's handle becomes here. So the concept of like this equivariant is also sort of kind of behavior that exhibit out of these policies. Yeah, and also it's a way for you to test robustness. Yeah. So I think coming back to Colosseum, I would like to talk a bit about it. We realized that actually SAM2Act is really robust. So the way we measure is we have the original task without any perturbation. We have the performance for that individual task, and then we perturbate in a systematic way by changing different variations, and we try to measure the difference. And when we average it out, we realize that SAM2Act only have a performance drop of minus 4.3%. That's as close as maintaining. I wouldn't say as close as zero, but it's pretty well. That means no matter how you change the environment, how you perturbate the environment, it's still able to get a task succeeded. So I think that's something that is a huge gain. And
okay. Why do you have two that actually perform better under randomization?
Yes, that's a good question. So I think this is something that when we first designed the task, we realized that this is a problem, because for the two that performs better, because we are aggregating relative to like those that has no perturbation. So it's a average drop between the one that has no perturbation. For these variations, sometimes the no perturbation has lesser. So if you look at Colosseum, it's like basically a spreadsheet, and you try to fill in the spreadsheet. But not every variation, every task will have. So some tasks might not have some variation, or some variation might have less tasks. So that creates this like I guess when we design Colosseum, we should have thought of that ahead of time. So there is like this kind of weird phenomenon that occurs where if the model performs really bad on that task, and then if there's somehow in the perturbation it does slightly better, the change becomes magnified. Yeah.
Okay, that makes sense. Yeah.
Yeah, but at the end of the day, I think what we really matter is to look at the aggregation here of the average. Yeah. So I think that's one huge plus point about SAM2Act, which is it's really robust, and we show that both in simulation and we show that both in the real world for our policy. Yeah. And
can I ask, like, for what kind of compute do you need, like, once you train the whole architecture, like an inference?
Yeah, so I think that's a good question, Michael. I think as much compute as you can. I think that's like what you
At inference.
You mean like during test time, is it?
Yeah, test.
So during test time, I think for like a real world evaluation, I think we evaluated on 4090. I think that's pretty much enough. Yeah, but for training wise, as much as you can get your hand on, that's the best. Yeah. And
how much data did you have at train time?
For training time, for real or for sim?
Both. For real. For sim. I guess for either.
For sim, the R bench 18 tasks, we train with like 100 demonstration for each task. We did multitask training, and then test time for sim was like 25 episodes of each task. Yeah. And I think one thing to sort of point out is that SAM2 image encoder that was used here was the base model, and SAM2 has a large model that we did not try. So if we believe that if we change that to the large model, the performance will go even higher. But I think ultimately, we sort of prove our point with SAM2Act itself. So I guess sometimes in robotics, like 2% change doesn't really mean that much. Whereas the memory thing is more interesting to actually investigate on. Yeah. So coming back to the next point, which I think the last feature, which I think is really interesting about SAM2Act, is that our variation, which is SAM2Act Plus, incorporates memory into its performance. So having the ability to solve memory tasks. And as I mentioned about the memory bench, as you can see from the result, SAM2Act Plus really increased significantly as compared to like SAM2, which has no memory stage training, and compared to like baseline is also significant. And in the in an ideal, SAM2Act should get 100%. I guess we get close to 100% as possible. But I guess as I say, there's a bit of like data imbalance here, which led to not meeting the hypothesized performance result that we expect. But I guess overall we do see that the performance is significant. Yeah.
Seems to me you need a harder task for your memory bench now.
Yeah,
100%, 99%.
Yeah,
you definitely
that's
harder memory. Task.
Michael,
which
what
is a good thing.
Yeah, you're right. I think we do need a harder task for the memory bench. But also, I guess it's also a way for people to test, how far is current, BC policy away from the upper bound. So that could also be a way to look at this, right? So I mean, like, we are not claiming that we solve memory bench, because we basically formulate a problem and we show that this is the upper bound. But essentially, people can come up with ways to hit the upper bound, but still have better performance than us in generalization, in general task performance, or even I hope to see like a VLA model that's able to solve memory bench while be able to do all the other things. So I think that's the cool part. And I think one thing that maybe we can just take a look at some of the tasks from memory bench. So this is SAM2Act is able to sort of open the right drawer, and I guess like RVT. Sometimes RVT do succeed because like this is random. Like it's definitely able to succeed in doing the task, but sometimes you choose between which drawer to open. So I think in this case he got it correct. But if you look at things like, for example, put a cube, if RVT takes from the center and you press, it puts at the wrong place. You see, that's the very interesting behavior. And I guess like let's see whether ours works. Yeah, so this is SAM2Act plus. And I also want to point out something really interesting that I observed from some of this model is that they will try to put it in a way that, if let's say the cube is put in the center and if slightly tilted in a certain way, that sort of gives like a signal for the model to sort of hack on it. So they will try to use the orientation to remember, okay, where it came from. So that's something we find very interesting. So they're not using memory, but they're trying to hack this way through to optimize on getting the right location. Yeah, so that's why there's the variation in terms of what we expect the performance to be and what the real performance for the baseline is.
Interesting. Is that because like biases in the kinematics, the robot, like the motion? Yeah, okay.
Yeah, it's the bias in the motion, and also because the motion creates some kind of hints, so it knows that, okay, maybe I should put it back at that first point. Yeah. And the counter argument case is also, I think, is pretty interesting. So this one puts in the center, you press the button, and then it move to the left. Yeah. I want to show the. Can I? Sorry, I have to like to different screen. So sorry. It's kind of
so what's next? I guess what's the
So I think what is next? I think for us is to see how can we sort of incorporate this for not just like as what Michael said, right? This is like a short horizon task. I guess there's some concept of memory, but we ultimately we want to look at long horizon manipulation tasks, and not just manipulation. I think right now I'm really interested in mobile manipulation. And I think this problem, I think Chris has some work in this, and I think this problem is amplified significantly when it comes to mobile manipulation. And how do you represent memory in a mobile manipulation context? And I'm not talking about just finding the object and remembering the object and going somewhere else, but actually doing an actual task and then going to somewhere else and do something else and come back to do that same task. Are you able to sort of remember? So I think that's something that's really interesting, and hopefully we want to see whether can we take this and transfer that into mobile manipulation. Yeah. That's like the high level answer to what is next. So let me
makes sense. Yeah,
quickly share the last one. Yeah, so this is an example of like what memory task looks like in the real world. Okay, are you able to?
Yeah, we can see. Yep.
Can you see? Okay. So the idea behind this is that you have a cube in front of a button. So during training, we put the cube there, and then we remove the cube, and then the data that's collected is to press the same button twice. But during test time, we do the same thing, and whereas baseline basically choose between the red and green button. Whereas our model sort of remembers where the blue button was. The blue cube was in front of the button. So it's the same concept with like the breaking the Markov assumption, and to be able to put this in a way that requires some form of memory. Yeah, and I think this is pretty cool because I think this is what you expect in the real world, right? Because when you have someone interacting with a robot, the human might remove an object, and then will the robot be able to know where that object previously was, so that it can act accordingly? I think this is something that you can't just learn by throwing a lot of data at. So it comes fundamentally through the model architecture.
I mean, this is like the fundamental piece of like probably maybe one of the most useful robot apps that I could think of for a home robot would be like, where did I leave my keys? Which is like, which drawer did I leave my keys in? That
Exactly.
Right?
And you don't want your robot to give you a random guess.
Yeah, right. You don't want, exactly. You want to actually remember, or like, hey, where did I put this thing? Yeah, right. All of that. That's non-Markov, because if I put it in a drawer or something like that, right? It's I
feel that we want more reliable policies before trying to scale out these kind of foundation models for robotics, right? Because ultimately ChatGPT hallucinates. So I think VOA models could also, when it gets large enough and more capable, hallucination will occur. And I think a lot of times this hallucination could be exactly what you mentioned here, which is it doesn't really remember exactly where you put, and it's just making an educated guess. So I think that's like, yeah, that's the high level take. And I think that's all for my paper, and hopefully you guys find interesting.
Yeah, this is super cool. Well, so maybe just a couple of questions to round up on things, right, Jiafei?
Yeah, sure.
Let's say, if you have, let's say, 1 or 2 more months extension to the paper deadline, I'm sure there are things that you wanted to squeeze into the paper. What would you have done if you just have that 1 or 2 more months? Is it like to swap out to a bigger, like what's that, the SAM2 image encoder thing?
Yeah, I think that's a good question, Michael. I think more cool demos, I guess. No, I'm just kidding. But I guess these days there's a lot of hype about like cool demos. I think this kind of thing is really hard to do like cool demos, because when you do cool demos, you make the problem much more complicated, and you miss the the essence of understanding the fundamental science behind robot learning. So I guess like we want to make the problem manageable. So I think what I will spend time on sort of to investigate is one of the questions or some of the limitations that we mentioned, which is like the varying window length of the memory. And as you say, like what happens if you have a larger image encoder? And also to sort of further do more ablation study to better understand this concept of memory. And I think one of the problems that we also face that I think this policy could be better improved on is semantic memory. So semantic memory in a sense whereby do you remember which exact color? Because right now this is a lot of spatial memory, because the point has to be previously reached before you do that. And you realize every drawer is the location, but it's not differentiated by colors. So we want to understand, how can we learn semantic memory out of this? So there might be some fundamental architecture change that we need to implement, or there's other tricks to do that. And I guess humans have these different stages of memory: spatial memory, semantic memory, and episodic memory. So I think if we want to move more towards like robot learning policies that's human inspired, then I guess like these are some of the problems that we need to solve. I think this, and also like the ability to do like reasoning or failure reasoning and all these kind of things, I think is what I saw missing. Yeah.
And anything like super surprising or unexpected when you were doing this?
Super surprising and unexpected. I guess like the way as I mentioned, like how you see some of the policies, basically users leverage on its bias to sort of increase the performance. Like just a slight shift, or when they try to close the drawer, they don't close fully. So because if you don't close fully, then obviously
it's like a very lousy thief, Okay.
Yeah. So it's really interesting to see those examples, and that makes us think a bit more about how we should go about designing the task. I think that's like the hardest part. So a lot of time was spent in terms of thinking about how we should go about designing these tasks, how we are able to, and test out to make sure that, we are not just, I guess a lot of times, we have this like placebo effect whereby you think that the model is learning something, but actually it's not. So we want to make sure for sure that the memory component is being utilized and the model is able to, remember exactly what it done previously. So I think that's something that is really hard, and that took a lot of effort.
Very cool. Maybe one last question just to wrap everything up. Any great paper you read recently that completely blew your mind that maybe we should invite for our next guest? Any paper recommendation?
Oh my gosh, these days there's so many like really interesting papers, that came out. I think there's a paper that came out today, I think from Suran's group, Sura and Dosa, the universal video action model. I think that's really interesting.
This one, right? I think.
Yeah.
Cool.
Cool. Yeah, I think these are pretty interesting line of work. Yeah, I guess we can look. I mean, people are interested. I guess that really helpful.
Cool. Well, thanks.
All right, awesome. Chris, you have anything else?
Oh, I'm good. I asked plenty of questions throughout. This is a lot of fun. It was. Thank you for coming on.
Yeah, thanks, Chris. Yeah, it's good to see you virtually, and hopefully, I guess I see you a lot in the conference. So maybe we'll see each other again.
Thanks you so much, man, Jiafei. Really appreciate it.
I think this is a great initiative. I think it sort of educates people about robotics that's beyond just cool demos, and there's a lot more problems beyond. Yeah.
Okay.
I'm
excited about it. See you.
Okay. Thank you, Jiafei. Okay. Bye. What do you think, Chris? What have you learned?
Cool. I think it's a Cool paper. I like this kind of direction. I think setting these, there's a few things that I like here. The memory problem, like solving memory, spatial memory like this, I think is one of the bigger ones that actually prevents robots from like really being useful deployably. So like, meaning that like if a robot is actually supposed to be autonomous, if it's not teleopt or whatever it is, or scripted, like memory is like it has to have really good functioning memory. And so I think that part's really valuable. I really like a lot of the stuff with these spatially abstracted or whatever you want to call it, like these kinds of policies that aren't doing continuous actions. They're a very interesting kind of difference from the way that like a lot of the time we see people doing these. So like compared to like the way that you do a VLA, right, where you actually are predicting actions, right, discrete actions that to tell you how the end effector is going to move. That's not what happens here, right? It's based on, it's like the fact that
Keyframes.
the keyframe stuff, like there are downsides to that, like which we didn't really talk about, but there are also but like one of the big upsides is like the precision stuff, like the fact that he can with only a few demonstrations train like those peg insertion tasks. That's pretty impressive. Like I don't know. So cool stuff. The SAM2, of course, very interesting. Lots of like, it's interesting how complex the training architectures are getting, with some parts being frozen to get the vision encoders right and all that. Anyway, yeah. What about you? What do you think?
I mean, for me, definitely the memory thing, it's great to see. I guess as a layman, all these Markov decision thing, I vaguely know what they mean, but I think just looking at the baseline, it's not even like to a human, it's such a simple task. You don't even think of it as memory. You just do it. Like, you know, but it's so difficult for an AI right now. So, but it also points to me like, I mean, even like this is already SOTA result, right, in some sense. But you look at some of these, like, firstly, the task to a human is very, very simple task. The other thing is also like the success rate. You're talking about 80-something% in simulation, 70%, let's say in real, right? You know, human were to do it would be 99.9% at least, you know. So, it'll be interesting to see what other type of like you know, research leaps that we need to get to that.
Yeah,
definitely the memory part is the most interesting to me.
So yeah, the Markov, like the Markov thing. So we talk a lot throughout the discussion about Markov, and so like I think it's probably worth including some summary of that, or like a discussion of what does Markov mean? So so in this context, what we're talking about is and this is true of most learning from demonstration stuff, right? Like you have to make sure that the image that you are capturing actually tells you exactly, like contains all of the information that is necessary to determine where the task is going, right? Like, and like technically this isn't like technically it's not, but like it's not always like technically true, because you have like long LSTMs and stuff which have memory, or like transformers can have like memory and video all that kind of stuff. But like in general, like for the best results, like you really are setting it up so that like at every frame you can tell exactly what's going to happen next, right? And I think that's the big thing that he is talking about throughout this, is that like the fact that from an individual image, if I look at my image, if I even look at it like a short snippet of video, right? Like I can't always tell, I cannot tell what is going to happen. And that's why, you know, that you actually need the memory part. And that's I think, I think that it's interesting. And I agree, like a lot of the tasks are quite simple. I will say, I think that a lot of the RL bench tasks are actually quite hard for robotics and behavior cloning. There's a whole discussion you could have on like what benchmarks are useful. And like he chose one where it does require a good degree of precision, right? And that's why for a lot of these methods, they perform pretty poorly. They're also a lot of the demonstration data is generated via motion planner, not via human data, which is like, so there's lots of like big discrete switches and stuff like that, which also so like there's a lot of little things in here that are like just different from other papers, I guess.
Cool. Well, okay, cool. Well, great to do this. First one, get it out of the way. We'll push it out soon, and then we'll do this weekly. Yeah. Hopefully we'll keep this up.
Sounds fun.
All right.
Yeah, I'm excited.
All right.
I'm very tired because it's after midnight, actually.
Oh yeah, that's right.
I'm pretty fuzzy.
All right, cool.
Yeah.
Let me pause the recording.